Good morning. Today we're going to talk about large language model functions, how to use those with Elastic to generate smart query experiences. The pattern that we're going to walk through today came from one of my peers at Elasticsearch, a gentleman by the name of 𝗦𝗽𝗀𝗻𝗁𝗲. He's what I would call a search relevance wrangler. He gets into the deepest, most challenging search relevance challenges, and he solves them. Now, I knew about this pattern, or at least I thought about this pattern with peers prior to even joining Elastic. But in March 2025, I saw the first pieces of code for it. So this is a relatively new pattern, not something that a lot of folks are doing, but it's incredibly powerful and very flexible in terms of delivering results and high-quality search by leveraging a large language model and depending on GPT-4 models to augment search and make it better. We're going to run through quite a few things today. We've got the setup. Why are we actually using GenAI with search? The end-to-end provisioning. Mike's going to walk you through how to actually go from we don't have anything to we have all the Azure resources we need to actually pull this pattern off. We're going to talk about OpenAI function calling. We're going to get deep into that, explain how semantic kernel is wired into this pattern so that you can actually replicate it with your own C# code. We're going to get into how the large language model uses Elastic to actually invoke search templates and execute queries on the back end. I'm going to do a live code walkthrough with Python. And it's going to be interesting because we're actually going to run this notebook live. I don't have any data in the system, so we're going to do everything from scratch and see how that goes. And we're also going to walk you through a live search on the .NET Core application. We're going to close out the technical bits on this pattern with a rundown of some of the advanced hybrid search techniques that we used, and then also our take on MCP and what Elastic is doing with that. Lastly, I've got Microsoft peers going to deliver an amazing message about some exciting stuff that we're partnering and working together on. So we've got some exciting news about the AI Foundry service stuff that we're building. My name is James Williams. I'm a search specialist with Elastic. I've got 2 years of experience with vector search. Prior to that, 2 decades of experience with enterprise application architecture. So I've been writing code for a long time, and my focus is transition to vector search. Mike?
Hello, everyone. My name is Mike Richter. I'm a principal partner solution architect at Microsoft. I work in the partner organization. I get to work with great partners like Elastic. Looking forward to talking to you today.
We've also got some product folks from Microsoft. We've got Rohit and 𝗦𝗲𝗀𝗀𝗲𝗲. They're going to talk about the new announcement that we have, so you'll get insight into that later on in the session. When it comes to this pattern, we're going to use a pretty simple use case. I'm looking for a home, but instead of trying to guess the keyword search parameters that I need to put into the search box or using filters and using a standard search interface, I'm going to type in natural language. And I'm not necessarily going to be great about the words that I type, and I might use abbreviations. I might not actually specify the exact location of the property that I'm looking for, but I'm going to provide enough details for the large language model to do some work and potentially try to give me a high-quality response. First thing that large language model is going to need to do is it's going to need to take that request, parse it into the parameters that match up with what it might want to search for. So I'm going to extract things like bedrooms, bathrooms, home price if someone specified some sort of high-end or upper limit on the price that they want to pay for the property. Then we're going to try to triangulate on the geolocation. See if we can get a lat long so that we can do a search that pulls back properties that are within the vicinity of the property search for the user. Lastly, we're going to invoke the actual search. Now, this is where things get interesting. We are using an Elasticsearch template that can take these properties, execute a structured query. Now, the structured query has a lot of flexibility to it because we could pass any number of parameters in. We've got natural language. We want this query to be semantic in nature. So I'm actually going to do search based on all of the query and potentially return results based on full text search, semantic search with vectors under the hood, and also filters, which is pretty much world-class leading search nowadays. Now, I'm going to pass it off to Mike, but before I do that, first high-risk maneuver. I'm actually going to run this notebook that should populate an index.
All right. What's that?
Can you talk about it?
Yes. There you go.
Can everybody see a screen that says index management? Can everyone see there's no index? Now, this is where things get interesting. If there's no index when Mike stops talking, we got some problems. I'm going to actually run a notebook that populates this index with data. And there's a lot of stuff under the hood we'll walk through in a few minutes. But I'm hitting the run all button. And I'm really hopeful that everything works. And we're not even going to, just go, Mike.
All right. You ready?
I got my fingers crossed, and hopefully we're in good shape.
All right. So I'm going to talk about the exciting part of this is all the Azure infrastructure we need to make this happen. So we just kind of walked through that theoretical, okay, if we're going to build this LLM-powered search and we're going to use geocoding to get longs and lats, that's great, but what do we need? Right now we have nothing, right? Well, you have your index that you're going to be demoing with, but right now we have nothing. So what's great is we can get all the infrastructure that we need to deploy this on Azure. And Azure also makes it easy for us to build this in a secure way, a performant way. If you are building enterprise LLM-based search applications, all of those features that you need for security, compliance, we could build as well. So I'll show you the Azure resources that I've already deployed to make this happen. So I'm going to zoom in here a little bit. You can see that I've got my Elastic, right? I also have Azure OpenAI. So we're going to be using Azure OpenAI. And what's great about Azure OpenAI is that you get the same 8 OpenAI models that you get with OpenAI. So everything we talked about in the keynotes this week, all the models, right, they're available on Azure right when they become available on OpenAI. So you get access to those automatically. But it's not just about the access with Azure. Has anyone here deployed Azure OpenAI? All right, so a bunch of people. For those who haven't, what's great about Azure OpenAI is all the enterprise readiness that you get with it. So you can use Azure's managed identities to authenticate to OpenAI. You don't have to worry about passwords. You can lock down OpenAI to a virtual network, keep all the traffic private. So you get all the great innovation from OpenAI, and you get all the great security, governance, compliance features of Azure, okay? You also see here that I've got an Elastic cluster. This is a managed Elastic cluster. It's managed in Elastic's cloud, but it's running in Azure region, right? So we can keep all of the traffic in Azure, but you get the benefits of Elastic's managed cloud. And you can see the way that I've named this from my deployment. I've got this Azure Search JCV2, and if I go into my Elastic cluster, you see it's the same thing. So if you are an Elastic customer, use Elastic Cloud, this will look very familiar to you. So I could deploy this all through Azure. And what's really nice about this, again, I get, because this is through Microsoft's native ISV service, I get to also use, I get to lock down the traffic to certain VNets using private endpoints. I can also use my my Microsoft commit spend to buy Elastic. So you get all these nice benefits, and you can automate it. You can automate the deployments. Let me show that really quickly. Who here are familiar with bicep files? Azure bicep files? Okay. Most of you, right? You can deploy this entire solution with a bicep file. I broke out the Elastic piece here as well. So all this is automatable. So if you're going to be building these LLM-powered search applications and you want to be able to do dev test, you want to be able to have these a full kind of end-to-end test as part of your CI/CD pipeline, you can make it all happen with Elastic as well. I've got an Azure Maps account in here too. That's what we're using for getting the longitude and latitude of the locations. Container app service. So has anyone here used Azure Developer CLI? AZD up, AZD down? Okay, so some people. So in the repo that we have, we'll show the link at the end. We have all the code here. You can just do AZD up. It'll provision all this infrastructure. It'll deploy the sample app that we'll show later to container apps. So you can get all this working. And then, of course, you get AZD down when you're done. And I think now that I've showed you the infrastructure, hopefully your notebook has finished processing. I'll hand it back to you so you can show them all that.
Sounds good. Thank you, Mike. If we could switch back to the slides real quick.
Yep.
I'm going to give the notebook a little bit more time to bake, but I think it actually worked, so fingers crossed, we'll see. Before I get into the notebook, it's important to kind of give you the secret sauce up front of this pattern. So obviously this is a coding pattern. It really centers around getting the LLM to extract the information from the query and populate a search template and execute the search. And then if for some reason we don't get results, we're going to execute the search again with less parameters until a point where we actually get results. So we're really trying to be smart with this query execution. Make sure we always return results. The way that this works is you've got Azure OpenAI that is responsible for creating those parameters. And it needs to know the structure. But if you tell it what the structure is, it can extract the search parameters in a very consistent, deterministic way. It's one of the reasons why a lot of LLM-based query rewriting doesn't work, is because this particular component is not present with folks when they write their code. If you have those parameters parsed properly and you have a search template on the back end, you can have a much more specific query to Elasticsearch that invokes all of the logic needed to return the results back. The Elasticsearch template, it's not just a static thing that doesn't have a lot of configurability to it. It allows for you to have optional parameters. It allows for flexible filtering. So we don't have to filter on all of the properties like bedrooms and bathrooms and features. We could just focus on houses that match a specific bedroom count. If the user doesn't pass a bathroom filter in, then we won't assign it to that. And the search template's smart enough to basically toggle off query logic when appropriate. One of the last components of the search template that I'm a big fan of, and you'll always see me try to introduce vector search into my use cases, is the hybrid nature of this search. It's not just full text search. It's not just filtering. It's vector search combined with that to deliver the best relevance. The goal is to have something that's reusable and consistent. So we may not have C# developers that know all the intricacies of Elastic Query DSL, but we can tell the large language model, execute this search template with these parameters, and it will do what it's supposed to, and we can reuse that template. We could potentially wrap that template in an MCP server, make it available to others. So I showed you, well, I didn't actually walk through the notebook, but I executed the notebook. What did I execute? What did I try to set up? So Mike showed you all the infrastructure paved and exactly how you would do that in infrastructure as code. But as a developer, just trying to create a sandbox environment to show in front of an audience, and me being a developer, not really having respect for production grade systems, I have this notebook that does a lot of the things that you need to actually set up Elastic. So empty Elastic cluster. First thing I need to do is set up ML inference. I'm going to use Microsoft's E5 model so that all my semantic text fields can have ML inference. Second thing I'm going to do is create the search index. Now I've got all the properties, number of bedrooms, bathrooms, property features. The description fields, those are the semantic ones. We're going to turn around and copy those to a semantic text field in Elastic. That's a relatively new feature that allows us to generate vector embeddings automatically. So as you ingest data, the vector embeddings are getting generated, and it makes it super simple for you to add vector search into your applications. Next thing I need to do is create a search template. This is where I specify exactly what the search behavior is going to be, specify the precise Elastic Query DSL, save it in Elastic cluster so that any time an LLM wants to invoke that, it just refers to the search template by ID, passes the parameters in, and I've got this very advanced search happening on the back end. The last thing is ingesting the data. We've got a JSON-L file that has all the properties records. We trimmed this down from the original data set to about 10,000 records, and we're loading them in batch size of 1,000. So that's relatively simple bulk load code, but it's necessary to actually populate the system with data. Can you toggle me to the demo and see if we can make this thing work? Yeah, mine. So we're back to the index. There's data. That's good. We're 1 for 2. Hopefully the next part will work. I'm gonna actually discover this data. Y'all don't know what this data looks like, but we've got property records that have your standard things. The geolocation, the home price, number of bedrooms, all that stuff. The more interesting thing to do, though, is to actually visualize the data in a map. So since I have geo coordinates, I can use Kibana to drill in on where my properties actually are. And as you can see, some of you might know this, but I'm a Florida boy. Look at all those properties in Florida. We're going to do our search in Florida. We're going to see if it works. Because we got a lot of properties in Florida, we should get some hits. So good news is everything worked, and we've got data in the system. So really, it's just a matter of kind of moving forward. So before I actually demo, I'd like Mike to walk through the semantic kernel code and some of the cool stuff that we built with C# and the prompts on the GPT-4o side. So I'm going to go ahead and hand it back over to you, Mike. And
all right.
With any luck, when we get back, all the cool code that he showed you is actually going to work when I try to demo it.
All right. So is my screen up? Yeah. Okay. So so James just showed you. We loaded all this data. We used all this really neat features in Elastic, like the semantic fields and all that, to embed on the fly as we got pulled in. But how are we going to actually work with this, right? We have all our infrastructure, right? And so that's where the code that we wrote comes into play, right? And so to make this work, we're using the recently GA'd semantic kernel agent framework. And so I'll walk you through what we did here really quickly. You can see here, line 35, we instantiate our semantic kernel, right? We're telling it that we're going to use Azure OpenAI, right? This is the model deployment that we're going to use. You see I'm importing some plugins. I'll come back to that a little bit later. But here's where we define our agents, right? And you can see that we have to give our agent a name, a description, some instructions. I'll show that in a second. We have to give it a reference to our kernel, and then we have some arguments that we're setting for Azure OpenAI, right? So we set the temperature to 0 here because we don't want it to be creative. We want it to be as we want it to be as simple as possible. Our agent is just going to be taking a user's kind of human language text and turning that into search parameters and doing the search, right? So we want this to not, write poetry or do anything creative for us. We want it focused on that mission, okay? And so in our prompt here, this is our instructions for the agent.
There's a lot of instructions there, Mike.
There's a lot of instructions. You wrote most of these instructions.
I sure did.
So we tell it, you've got all these plugins available that you can use to satisfy the user's query, right? And then we want you, because we want to actually output this into a web application, here's the schema, here's the JSON schema that we want you to return the data in. And if I go back to the back to our agent definition here, you see at the semantic kernel level, I have all these plugins registered, right? I have a geocode plugin, right? That's just the code that's going to call the Azure Map service and say, if my location is Madison Square Garden, I want to get back my longitude and latitude, right? Then I've got this parameters plugin. So when someone says, hey, I'm looking for a 2-bedroom apartment with 3 baths, we can find all of those parameters. And of course, we also have our Elasticsearch plugin, which does the actual search. I'll just show the Elasticsearch plugin really quickly. Elastic has NuGet packages for .NET, right? It makes it super easy to build Elastic applications in .NET. The front end we're going to show you is a Blazor application, so .NET and Elastic work great together. And the other thing I want to show is, if you look at my plugins folder here, you see for all my plugins, I've got the code, and then I have interfaces, right? So if you're .NET developers in here, anyone .NET developers? Oh, great. So everything you do in .NET with your registering your services, all the dependency injection, right? So you can have your entire the way that you're used to working, building unit tests, right? Mocking out the services that you're not testing. You can use all of that, and also semantic kernel and semantic kernel agent framework. So I just like the way it all comes together. And what's really nice also about semantic kernel is the modularity of this, right? So if I go back to my agent here, imagine if we wanted to extend this demo and add something like school data, right? If I'm looking for a home, or if I want to plug in an office that I work in, what's the commute time, right? I can just add these plugins and they'll be available to my agent. I may want to update the agent's instructions so it's aware of how to use those different functions, but it makes it really easy using semantic kernel to add more functionality. And I think as far as the code goes, I know that's a ton of code that I just kind of walked through here, but maybe you get a sense of what we built. And I think in the slides you have the overview of it. So.
Oh yeah, so we wrote a decent amount of code, obviously, and the cool thing is we actually all of the entire application is .NET. So all the services, C#, we're using the native Elastic client to communicate with Elastic. And I think that's important because you want to make sure that you could stay in your native language. Now, we cheated a little bit with the notebook because we're just trying to get data into the system, and I'm a Python jockey, so it was just simpler for us to do that. I can tell you from experience, because I have had to do some work with control plane in the .NET client, we could have actually done all of this in pure code, the notebook that I stepped through, but we chose to do it the lazy way because I didn't want to actually port all of that over. But what we did port over are the real core components. We've got the Blazor front end, single page application. You're going to see it's a fantastic UI, probably the most interesting UI you're going to see the entire show. We've got a search agent service that, there's a lot of code in there, but when you invoke it, it really doesn't do a whole lot other than say, there's all these tools that I have access to, yeah. GPT-4o, like you decide what to do. Like, I don't know if you mentioned the auto setting, but the auto setting is what makes this challenging. We could have hard coded the instructions in code and not let the large language model do all of the work. But the goal here is to show you the power of the pattern. And the fact that we're letting GPT-4o do everything for us is noteworthy. And you're going to see in a second, if the demo works the way it's supposed to, how the large language model can change its behavior based on things that are happening with the tool invocation. So that parameter extraction, obviously, that's the first thing we want to see happen. But the Azure Maps lookup for the for the lat long, so we can triangulate on the geocode, making sure that the LLM has discretion in invoking that and passing the parameters in, and then finally the hybrid search. So we've got really 4 C# components under the hood and a Blazor front end to drive all of this. And like I said, I mean, we're really putting pressure on GPT-4o to do what it's supposed to do. This is the part that I've been nervous about for a while. I'm going to actually try to do a demo in front of this audience. And this will be the first time this code's been demoed live. Can we switch to my, I think I'm ready.
Got it.
Okay. I'm going to build the app locally just to prove to you that we are not cheating in any way, shape, or form. And with any luck, I'm going to get code spaces to pop up a little, hey, you have a URL that you can hit. That's going to be the Blazor front end. It might take a second. And hopefully I'll kill some time by, a little bit of small talk here. I was kind of joking when I said the front end is amazing. When you see it, you're going to be like, oh yeah, these guys used to code back in the day, the early 2000s, and that was intentional. What we wanted to make sure of is that the single page application doesn't have. I mean, you've got these smart, chat clients and desktop clients that can do interesting things. And a lot of TypeScript-based systems where some of the logic's pushed into the front end, but in reality, what you really want is a back end that that actually does all of this work. Because I'm more of a back end guy than a front end guy, anyways. But it's taken its sweet time in firing up, but it hasn't aired out, which means that we may end up having a live demo today. We shall see. That's the backup URL. while this is running, I'm just going to hit the backup URL, see if we can get a result. This is actually the environment that Mike provisioned. So we've got a search here, and I'm going to expand it. We're just doing a quick search for 2 bedrooms near Empire State Building, and we'll see if this comes back while my dev environment is loading up. And sure enough, the search worked. So the good news is, even if my local environment didn't do what it's supposed to do, and code spaces hiccuped, which was the thing I was most nervous about, because internet connection issues and all of that. The cool thing is, this search is pretty sophisticated. It did pull a 2-bedroom apartment. It got the geolocation right. And if we just click on the tool invocations, look at what happened here. The fonts are a little bit screwy, but what we did was we actually executed an Azure Maps lookup. We extracted the parameters. The LLM extracted the parameters properly. And then it started searching, and that's where you see the multiple Elasticsearch chains. The reason why that search took so long to come back is because it didn't get a hit on some of the parameters that it passed in. So it kept trying the search over and over again until it got a search result. And then that gave us the actual result that actually matches as much of the criteria as we can for this pattern. So that's the fallback, and it looks like the application is still coming up. But the good news is that this is the long version. If I had typed in a search that was simpler in nature that got a direct hit, it wouldn't have executed Elasticsearch multiple times. So what I'm going to do is, while this is firing up, I'm going to switch back to slides real quick. And if this thing ends up...
Can I just show something real quick
yeah,
also?
Absolutely.
Right, to just go a little deeper on what you said, right? Earlier you said our function choice behavior here you see is set to auto, right? So it's really up to the model to decide how to use these functions, the geolocation, the search parameters, right? So that's your point. And then for all the different tool invocations that you saw, said, okay, we're going to ping Elastic multiple times, right? Being able to log all that, that's where this function invocation filter comes in. So for all the different functions that get called, we can kind of intercept that. So before the function gets called, we can see what the parameters get passed in. Then after the function is called, the parameters that come out. So this makes it really nice for when we are developing the application, and we could see how the model is calling these different functions. So, yeah.
Cool. We'll double back to slides.
Right.
So what was happening under the hood? How did we get to the point where we were able to execute multiple Elasticsearch calls and still get good results? Well, the power of linear retrievers kicked in here. So what we did under the hood was we executed a search using a new capability in Elastic called linear retrievers. What it did was it did multi-match search, basically a full text search, and a dense vector search after applying the filters. So we've got basically two different queries running simultaneously. We take the results back, we normalize them, and this is where linear retrievers are powerful, because when you have different search techniques in Elastic, they don't all do the relevance scores the same way. So we introduced a normalizer that allows us to actually say, all right, we're going to take the scores that come back from these 2 query blocks and we're going to make them even Steven. Then I can turn around and apply a weighting to those query blocks and say, look, the vector search, it's not as important as the full text search. If I get a full text search hit, I want the score to be higher. So it applies a heavier weighting to the full text search component. Now, we specified this in the DSL. You could have switched the weightings if you wanted the semantic search to have a higher weighting. But a lot of times you're going to have one or the other be more important to you. Then we re-ranked the top documents. In this case, the rank window size is set to 100. So if we had more than 100 results back, we would trim that to the highest 100 results. And then we turn around and say, OK, well, we're just returning 10 results. We're going to take the top 10 scored results and return those. So under the hood, that's how we're actually able to get really good search relevance for that query. Now, we're going to kind of wrap things up. We talk about MCP all the time at Elastic, and you probably heard the word MCP a million times this week. We didn't use MCP for this specific demo, and my peer Sunil actually has ported a version of this over to MCP. The reason why we didn't use MCP is because 2 reasons. First of all, the MCP implementation we have is TypeScript. We wanted to do something in C#. So that's point number one. And then second, there's no support for search templates. So if we had support for search templates, we might have gone that route. But what we ended up doing was just using straight semantic kernel and C# code. My prediction is that down the road, you're going to see functionality like this wired into the search platform. And we're working on a lot of cool stuff at Elastic to try to bring search relevance to the forefront and make it a lot simpler. I didn't go into a lot of detail on semantic text. I may toggle back to that in a second just to walk through that. But semantic text is one of the killer features within Elastic that allows us to make it super easy to introduce vector search and auto-chunk your data, and all that's happening under the hood. So you could think of MCP just being an extension of trying to make the search easier. Less work for you to do to get search experiences. So what are the key takeaways? Other than .NET Run in code spaces doesn't work when you need it to work. Although it worked like 1,000 times prior to this session. So I'm going to tell you right now, I love code spaces, and I had enough confidence to trust it live. I'm sure it was the internet connection or something else, because I swear to you, I never had any issues with that app coming up local on my machine. But key takeaways outside of that are, Azure OpenAI is really good at taking natural language and converting it into query parameters. And that's one of the key elements to this pattern. The second is that when you wrap the things that the large language model needs to do in tools using semantic kernel, you can really expand the scope of what you do. Add capabilities like a specific map search before you invoke a search for the back-end data. Code spaces, which I mentioned earlier, I did all of my development work in code spaces. I tend to do most of my stuff in Python and VS Code, but I took the leap, and it did not disappoint outside of that one call. The thing that I really like about it is it blends the best of all worlds. I was able to do my Python notebook stuff in Python. I was able to start writing C# code. I hadn't written C# code 10 years, so I was like, wow, this is really cool. The IDE is awesome, and it's in my browser tab. The source control being kind of tucked in and just part of the platform, along with being able to build and deploy without having to worry about installing or running containers on my environment, made this a really good, easy way to kind of port that over from Python over to C#. On the Elastic side, I represent Elastic. I've been saying this for a while, and if you stop by the booth, you'll hear me say it again. We're the best vector database, period. We are the best vector database. And if you're building GenAI experiences that require search retrieval, you should be thinking Elastic first. Yeah, you should be thinking Elastic first. When it comes to the reasons why, it's because we take core search functionality that we've been doing for over a decade and doing really, really well, combining it with vector search and doing semantic search better than anybody else. And then the ML inference is just icing on the cake. You don't have to worry about a lot of the things that the past generations of GenAI developers had to think about. You can just use the product and get good results. The last thing I'll say is I do believe that Azure is the best cloud platform for both developer side and the operations side. And I'm super happy, to be here today with you, and super happy about the announcement that we're gonna dovetail into. In terms of resources, we put together some resources on the Azure side and the Elasticsearch side. So these are the key links that we used, in terms of documentation for our code to build this pattern out. And the very bottom is the actual repo. And we will be posting a blog on this soon, so that all of the code associated with this can be replicated, and you can see where the real faking out happened. Like, where do we really hard code something? And hint, we didn't hard code anything. So when you go to run the GitHub repo, you'd be surprised that we actually didn't fake it out. Now it's time for me to turn it over to Mads, and he's going to talk about our exciting initiative.
Baton pass, and we also have Rohit on the screen, on stage with us, and we are here to talk about how we are going to be integrating Elasticsearch with Azure AI Foundry. This is my third session where I've talked about Azure AI Foundry and the agent service. We really believe it's the agent factory, where you have this whole life cycle where you can pull in your models, add in your knowledge and tools like Elastic, have the agent orchestrate it, and then also have the developer tooling for you to observe it and ultimately trust whatever you build and deploy. Now, we keep going. If we take a look at what Foundry actually is under the covers, it's all those bits and pieces that are necessary to support that full lifecycle with models at the top. The service that I own right now is that middle layer, the Foundry agents, which is actually orchestrating with the models all of these different tools like Elasticsearch. And if you haven't been hit over the head already with what is an agent, of course it's just an LLM, some instructions, and some tools, and you saw them use semantic kernel to combine all of these pieces together. Now what's missing today, and what we're excited to work with the Elasticsearch, is their tool isn't natively integrated within Foundry. What they had to do, and what all of you would use today, is semantic kernel. Because that is the Microsoft's enterprise AI SDK that basically lets you connect with anything. You got to see them use it connect to Azure, OpenAI, of course to Elastic as a memory service, and they're also integrating with a bunch of agent services. Obviously, Azure AI Foundry agent service, but even those from our competitors, like Google using A2A or Amazon Bedrock. It's this glue that you can use to talk to pretty much everything. We have a goal, though, within Azure AI Foundry to bring every single one of these logos out of the SDK. We'll leave them there, but we'll also bring them in to Azure AI Foundry as a managed service. So with that, I'm going to go ahead and pass it off Rohit to talk about what we are planning on adding to Foundry Agent Service to integrate with Elasticsearch.
Thanks, Matt. So along with what Matt just talked about on the AI Foundry side, Elastic has also been an Azure native partner. So what we're doing here is bringing the best of both together. And what that actually means is that via the integration, the semantic kernel integration that Matt just talked about, Elastic will now be available very seamlessly as a vector store, as a knowledge base in the Foundry portal. Elastic, through the semantic kernel integration, will do the initial kind of the data plane integrations. And once that is available, this is now what you see is the Foundry's knowledge base portal experience. Once Elastic has implemented the semantic kernel integrations, we will now be able to bring Elasticsearch as an option on the portal. Now, this requires some work on the Foundry side. It also requires some work on the Azure native side to really make this entire experience very seamless. And we're not just stopping here. So as I mentioned, we're bringing kind of the best of both worlds on the Foundry side and Elastic being used as an Azure native offering. So what does that really mean? A customer can go to the Azure portal and use the Elastic service not just as a vector store. They could use it as a log-based system. But eventually, the goal really is then to say, hey, as you're using Elastic through your deployment process, can you seamlessly through the Azure portal, through CLI, through SDK, bring Elastic as a knowledge source? And it is as easy as bringing in Elastic via the dropdown through the portal. Again, this entire functionality will also be available via CLI, SDK. But the goal here is, how can we make this journey for an end user, for Elastic users, for Azure users, for Foundry users, as seamless as possible? And this is really bringing all this together via this one example with Elasticsearch. So yeah, with that, I think we have reached the end of the session. I think here are all the different breakout sessions and related updates. And we're here for any questions, any other thoughts you may have. Thank you.
And if you have questions, we have a microphone up front that you're able to go to, and we'll go ahead and get them answered.
Hello, my name is Joe. Welcome to my public humiliation, and I'm a non-coffee drinker. And we've been using Elasticsearch just we talked, I think, on Monday, and I was just curious. If it doesn't go within the scope of this discussion, I apologize. Just curious about the provisioning Elasticsearch using ARM processor in terms of the pricing difference between what is in the cloud using Microsoft resources. Can you speak a little bit about that and maybe educate me if anybody else has that question or set me straight?
When it comes to pricing differences for ARM and other chipsets, we charge based on elastic compute units, so we don't discern between ARM or other processor types, and we don't run on GPUs yet.
Okay.
So there's no pricing difference there.
No, I think we meant ARM. You meant the Azure Resource Manager, right? Deploying.
Yeah.
Yeah.
Oh, sorry.
So yeah.
I heard ARM. And I was like, oh.
No, so you're asking if I deploy through Azure, right? How is that price different than if I were to deploy through the Elastic Cloud Service? Is that? I don't know all the different pricing nuances, but
it's going to be elastic compute.
there's no difference. Well, there you go.
It's elastic compute units. We don't.
Then I'll shut up. Thank you.
Yeah. we don't.
Thank you.
Same answer. I just interpreted the question wrong.
Any other questions? If not, thank you for the really great demo. Azure building agents. I know we've talked about RAG over the last, I don't know, is it 2 years now? It's wild. Time flies. And you had to really use things like Elasticsearch to pull in that data so the agent could answer your questions. And that was kind of what this demo was all about. As you start having agents actually perform real automation, it's easy to go, that's old stuff. I don't have to worry about giving my agent context anymore. It's all good. But for your agent to perform an action, it has to know what it's supposed to be doing, what is it going to be filling out a form for, how does it know that it's actually doing the action correctly, and it makes using vector DBs like Elasticsearch even more important, right? So if you haven't already built your basic RAG application, start now, because it's going to be a required skill set as you start building these more automated workflows with AI agents. Awesome.
Cool.
Well, thank you again.
Yeah.
Thank you.
Great.
Thank you.
Thank y'all.
And I hope y'all enjoy the rest of the build. Cheers, y'all.
Thank you all.
Thank you.
Nice job. Nice job.